Welcome. I am going to try to do a quick review on some of the properties of Sn1 and Sn2 and maybe E1 and E2 reactions for the sake of people taking Organic 1, especially people studying for a final. So this is jumping straight into chapter 6 in the and at least the book I was using, Organic Chemistry by Wade and Simek. But so first off, we need to remember almost all organic chemistry comes down to one simple fact: acid-base chemistry, and 90% of it is that. There's some oxidation, there's some reduction, but it all comes down to Lewis acid, Lewis base. Lewis acid is an electron-poor electrophile, essentially. Lewis acid is atom missing electrons, wants those electrons. That's pretty much electrophile. A Lewis base is electron rich, willing to give them to a Lewis acid, something that is electron poor. That is your basic nucleophile. The only thing that separates a nucleophile from a base is that a base removes a proton. It essentially donates electrons to a hydrogen atom. A nucleophile can be attracted to any sort of nucleus, not just a proton. So first, what is Sn or nucleophilic substitution? Nucleophilic substitution is the generic reaction in which we have a leaving group. So we have a leaving group. And we add a nucleophile given as Nu. Sometimes negative, doesn't have to be negative, but it replaces our leaving group. And we have a leaving group floating around as the byproduct. Now, this can happen one of two ways. This can happen either by a first order or a second order reaction. A first order is Sn1, or second order is Sn2. What is the order? Order is the kinetic rate. How does this depend? A first order reaction depends only on one component reacting. A second order reaction depends on two components reacting. So what does that mean? We could undergo two possibilities for the same reaction. So right here, now we could have first we lose the leaving group, and then the nucleophile joins, and that's the slow rate determining step. Or it happens all as one step. And this is it happens all as one step. And this has big implications. The main implication has to do with chirality. And that if this is a one-step reaction, we're going to see, as we'll see, a inversion of the chirality, assuming that a version of stereochemistry, assuming that this is a chiral center. If it's not a chiral center, it's not really important. But if it is a chiral center, we're going to see an inversion of chirality. While the first step, because it forms a carbocation, means we could have a racemic mixture, meaning a mixture of chiralities. And if this was R before, it's going to become S. If this is R before, on the top version, we're going to get R and S in equal mixtures. So we have to pay attention. But for the most part, they're generally the same. So how do we separate these two? Well, if I call Sn1, what are some properties of Sn1 versus Sn2? We already said this is a first order, this is a second order. When we have the nucleophile is generally a weak nucleophile. The same way as you might have a weak base. Something that is not particularly polar, maybe doesn't have a ton of electrons, maybe isn't super electronegative. And then this one's going to be strong nucleophile, something that absolutely wants to act as a base, something that's going to be really strong. So the difference would be, for example, water is a weak nucleophile, OH minus is a strong nucleophile. One of these has a negative charge, one of these is neutral. Water can still attack, but is less willing to attack in that it is stable as it is, while OH is a little bit less than stable. The type of carbon it is attacking also depends on which type, and this has to do with carbocation stability and steric hindrance. If there is big and bulky groups blocking attack by the nucleophile, that is not going to happen in the rate determining step. So typically tertiary and secondary carbons undergo Sn1, but methyl groups, primary and secondary secondary halogens and other things with leaving groups will go in Sn2. So you notice secondary will happen with both Sn1 and Sn2. Secondary, slightly stable carbocation, but also not so sterically hindered that it's Sn2 is impossible. So that can be either or, depending. Now, the solvent can also help this. You want, in this case, a less polar solvent. Less polar and aprotic. So, aprotic means without a proton, without an acidic proton. So, no water, for example. This one, you want good ionizing solvent. So, a polar and protic solvent. Water or maybe even alcohol would be a good solvent for this. Something that's essentially going to be very good at stabilizing this carbocation. Well, a less polar and aprotic solvent is not going to stabilize the carbocation, therefore helping to disfavor Sn1. The idea is you want to disfavor Sn1 or favor Sn1 depending on what you're going for. So Sn2 always has an inversion of stereochemistry because it is going to undergo what is called backside attack. It's basically as the nucleophile comes in the back door, the leaving group runs out the front door. The front door is too crowded. You can't jostle into the same way as the leaving group is leaving. So you're going to attack from the opposite side. And so with that in mind, it's going to cause the stereochemistry to flip. So if you have here a stereochemistry and we attack from here, well, if the leaving group's here, atom has to come here, and so they flip and go the other way. Now, another thing to note is that the last thing to really note is that with Sn2, because it's a one-step second order reaction. There's no rearrangement. Arrangement. While Sn2 rearrangement is often possible, and in fact is often common. Basically, if you have a chance to go from a secondary carbocation to a tertiary carbocation, you're going to see some sort of shift. Whether it's a hydride shift or a methyl shift, you're going to see something that's, well, probably going to be a hydride shift. So that you make a more stable carbocation. And so that's another reason why you got to be careful. Sn1 versus Sn2. Chirality on one side is retained. Chirality is flip-flopped in the other. Rearrangement is impossible with Sn2. Rearrangement is common with Sn1. So we have to watch out. So hydride shift could also turn this into a resonance stabilized carbocation. So now real quick, what are some examples of strong nucleophiles versus weak nucleophiles? So let's start with the weakest. So put weak all the way over here, strong way over here. So strong involves, say, as I said, they're polar, but not necessarily charged. Or if they are not good electron donors. F minus, you would think, oh, that is super polar. But the thing is, F minus doesn't really want to share its electrons. What do we know about F? F is good at taking electrons, so it's going to be poor at giving them back. Another guy, carboxylic acid. Those guys can be nucleophiles. All those are weak, and then we start to get, okay, there's Cl minus and carboxylates. And we got some sulfides, some various amines, so NH3 and RNH2. NH2, I'm run out of room already. Br minus. Going down. Start on the next row. Then we start to get more charge. RO minus. So alkoxide, hydroxide, tertiary amine, cyanide, what's that? The alkynyl anion, iodide. This is actually coming down to iodide. Some of these, the strong nucleophiles end up being what we'd call soft bases. Some of these are soft bases as opposed to hard bases. But that is coming into some inorganic stuff. But okay, RS minus, NH2 minus, and phosphines. So some of these are not immediately obvious, but why sulfide is better than an alcohol. That has to do with the hardness and softness. That essentially, the bigger these atoms are, the more polarizable they are. The bigger they are, the less electronegative they are. They have all these electrons that they can donate, and they're going to be willing to share. they're still electronegative, they're still charged, but they're willing to share them in a bond rather than bogart them to themselves. So the smaller, less polarizable, more highly charged guys are weaker. The larger, the highly charged guys are strong. So the smaller guys weak, the less charged guys weak, more charged guys than bigger guys strong. So still sometimes kind of hard to tell. But basically, if you get these bottom row, that's probably strong. If you get these top 2 or 3, it's probably weak. If you get in the middle, it's hard to tell. But okay. Now, the other option is E2. E1 and E2. Okay. All the time you could have Sn1 and Sn2. You could also have E1 and E2. E1 actually stands for beta elimination. And E1 and E2 follow a similar pattern in that these elimination, instead of seeing the leaving group come off here, we have a base. Base is going to remove a hydrogen. Let's see, beta to the leaving group, and thus cause a alkene to form. BH neutral plus X minus. So we're going to cause the leaving group to leave, but first we're going to attack and remove a hydrogen. That's essentially what's happening during beta elimination. So what is this? Once again, you have a few things. E1 versus E2. E1, once again, is first order, meaning the first thing that happens is the leaving group leaves. That's always the first thing that happens on the first order one. The second thing that would happen is then the base attacks the hydrogen and thus results in our shift, our forming of the double bond. E2, it once again happens simultaneously. So in E2, the big thing is it needs a strong base. It needs a strong base. But this one, base strength is unimportant, because once it's in a carbocation, the proton is a lot more willing to leave. The proton is a lot more acidic once you have that carbocation there. But E2, in order for the first step to kick off the hydrogen in the leaving group, you need a strong base to pull off a normally not very acidic hydrogen. Now, in this guy, you definitely want a product solvent. Why? Let's think about that. We want a strong base. What's going to happen in a strong base if you have a solvent that is acidic? Base plus acid cancel each other out. Your base is now destroyed by your solvent. So you need a solvent that will not accidentally acidify your strong base. Now this guy, an E1, you want a polar product solvent. Once again, because you're trying to stabilize the carbocation. Now, ideally, your base isn't going to attack your solvent, but that's why a weak base is okay. Weak base isn't going to attack the solvent, and it's only going to attack once we form the carbocation because, hey, it's once we lose the leaving group, it becomes very acidic, very willing to leave. Once again, we have what happens with the tertiary and secondary more often than not, and these guys could be this guy. Once again, primary, this can happen with all of them. Why not primary for the E1? Because the primary carbocation is not very stable. Now these guys, this can happen with the tertiary. E2 can occur with tertiary carbons because we are attacking with a base. The base only needs to remove the proton. It doesn't need to fit in there. It doesn't need to hang around. So it doesn't matter so much if we have an incredibly sterically hindered carbon, because we only need to pull away a single proton, as opposed to replace something and stick around. Now, no matter what, you're going to be trying to form Zaichaf's product. As we'll undergo we'll talk about this in a few seconds. Zaichaf's product. And this is going to be the more substituted product. But one thing to note is that this guy would always attack anti-coplanar. Once again, a backside attack from the halogen, from the leaving group. And this one, geometry don't matter. Backside attack with the E2 because we're still trying not to jostle the leaving group. In this case, when an E1, when you lose the leaving group, essentially the structure goes planar, and then you could do front side attack or back side attack. Once the leaving group leaves, the front door is open, the back door is open. But in this guy, anti-coplanar means it's across the other side. So if we have a flat molecule and the leaving group's up here, we must attack from back down here, opposite and coplanar. Now, once again, there's no rearrangements in the E2, and there's rearrangements possible with the E1 because we're allowing for the shifting of the carbocation. And really the only way you can get the non-Zaichaf product, it will happen, but one of the main way is having a big bulky base. And in fact, a big bulky base is actually a way to favor E versus Sn. Because it doesn't hang around. But so Zaichaf's rule, this comes from Zaichaf's rule. Zaichaf, essentially that literally the more highly it's more substituted double bonds are more stable. Bonds more stable But the way I like to look at it is poor gets poorer. So what does that mean? If I have this, and the base has an option. The base has an option. I can attack 3 hydrogens on the right or 2 hydrogens on the left. I'm going to attack one of the 2 hydrogens on the left. Even though the 3 hydrogens on the right, it's easier to get your anti-coplanar. It's easier. There's more possibilities of attack. It's less sterically hindered over there. But the fact of the matter is that base is going to attack hydrogen. The guy with the least amount of hydrogens loses a hydrogen. The poor are getting poorer. So we form, so take that, swing the double bond down, and kick that out. Now the Hoffman product is the opposite. It's a less substituted product. But in this case, this Hoffman product is the less stable. Now, if you get option, cis conformation is less stable than trans conformation. Once again, that has to do with steric hindrance. But you're always going to, at least with E2, you're going to form whatever conformation comes from anti-coplanar. So if I have an option of there's only CH here, I only have one option to attack. So we're always going to get, it's always going to depend on what we're losing where. Okay, let's see. Quick review here. Sn2 and E2 need strong base or strong nucleophile. B, that's a nucleophile. If it's a, if leaving group, if, well, you know, let me, if, draw. If X is halide, Sn is favored. Good. Bulky bases favor E. Now, why might that be? Once again, elimination. Bulky bases have to take away the hydrogen. They don't have to stick around. They don't have to hang in there. So if you have some like triphenylphosphine, oh, that's a good nucleophile, but it isn't going to be able to fit into most compounds unless that compound is like, say, a methyl halide. If it's a secondary compound or a primary compound, it's not. It can pull off a hydrogen, sure, but it cannot fit in there to do anything else. But, let's see. If you have a choice, Sn2 will prefer primary. They both kind of go for secondary, and E2 will go for tertiary. Now, Sn1 and E2 and versus E1, typically they're going to be our weak base, weak nucleophile. But temp favors E, elimination, due to entropy. That basically I'm just trying to figure out how to explain this. I mean, essentially, it has to do with the number of components in there, that entropy, the randomness of the system that forming a alkene and the protonated base and the halide slightly more interesting than slightly more randomness than just the nucleophilic substitution. So in hotter temperatures, we might favor E1 versus Sn1. One good example of this E2, or even one good example of this E1 is alcohol dehydration, and that's where I'm going to end this video. And that, if we look here, we have, let's draw this compound, HOH. We need some acid here, but this is a fast step. We're going to quickly pronate the alcohol, make this a good leaving group. Make this a good leaving group. So lone pair goes. Cha-cha-cha. This is our rate determining step because this is E1. So we've lost our water. So we have now carbocation. From there, we're going to regenerate our catalyst. So our water can now attack here. The electron lone pair swings down. We form our double bond and reform our acid. Basically, OH is not a good leaving group. What is a good leaving group? Water. We turn a strong nucleophile into a weak nucleophile with the presence of acid. That acid, where is it going to attack? Lewis says, something that may not be the strongest Lewis acid. Well, where is that acid going to attack? Maybe not the strongest Lewis base, but a Lewis base, the OH. So that's just an example of this E2 in practice. Hopefully this has been somewhat useful. Thank you for your time.